Continuing on with class number 8, we just described some section 3.4, where we had work done on a moving boundary in a simple compressible system. Inside there, they introduced the polytropic process, which is an important process, but it's not the only one. I want to take a slight detour from what I had put together. I think when I got to this point in putting the notes together, I was thinking they were going to go ahead and jump to the other processes but it seems a little strange to me that we start jumping in with this process. It is one of many processes, and let me see. I'll talk a little bit about it. Let's see. I'll go to my notes here. Just move the keyboard out of the way. There you go. All right. So first off, the polytropic. I always think of this as poly as being, well, you could have this polynomial, right? Maybe. I don't know if that's necessarily true. And I need to confess that I added these to the front of it, thinking, why didn't they do it? And then later read that they were purposely not saying that this is what this equals to. And I still don't quite understand why they're saying you can't have that equal to it. It is true, but I think it's a limited truth. It's only true under certain circumstances. But for right now, I would still think it's valid right there, because that's the integral from 1 to 2 of this right here. What we've shown right here, I've skipped over the math that's in the book. You could see the derivation yourself, that you can see as a general thing, that when you plug in this idea right in there, that it's a constant, you end up with P2, V2, P1, V1 over 1 minus N. Now, N is, of course, the superscript that's happening right in there. So you might have to do a little bit of math to calc to be able to get to this place right here, but not too much. But this is on a pressure versus volume diagram, which is this right here, PV diagram. This is what this path looks like. It has like this sort of arc to it right there. And noticeably, this is for an ideal gas, but it doesn't have to be an ideal gas. It's really just describing the behavior of going from one point to another point. We could by the way, we could go in the other direction too, either positive or negative. And whatever you might have here as your exponent, that exponent will change the shape. So I went ahead and plotted some of these out right here. And so here's like multiple ones right here. So here's like 0.8, and here's 1 right there, and then you can see that here's 0.14. So you can kind of change it. You could I made this one over here so you could start creating. You can go 2 if you want. You can see what that looks like. You go 0.2. You can see what that looks like. You can kind of see where the shape of the curve as you're making a path. That's sort of like the idea here, and we could kind of curve fit how that works. You might recall that we did something along those lines. We saw that we had earlier on. I'm trying to remember which video or which class it was, but I kind of showed that when we were plotting the thing. Oh, I know, when we were doing the ideal gas law, you notice that we had something and it was to the power. Let's see. Let's open that back up. That was like in class, right? The Excel sheets, and we did the compressibility chart. That was the compressibility chart overlay, ideal gas demo, right? So in the ideal gas demo, right in there, you could see that we had this path right here, and that let's see. I went to format my trend line. We could put a power and display the equation on here, right? And so it was described by right here in a pressure versus volume. We had some coefficient in front, but up here at the top we had and I think it was because it was, well, I won't give a reason for the negative in there. We had a power type of relationship right in there, and perhaps we could judge from that is the polytropic process. What happens if we go in with a negative number? What about a negative 0.5? What happens? Nope, doesn't like it. Interesting. Okay. Maybe change this. Reset. Okay, it had them curving the other way. Interesting. Okay. I don't know why that would be like that. All right. Anyway, so we're getting into this polytropic process. And what happens, though, if n equals 1, we notice that the thing is going to blow up, right? So that's no good for here. So we have to go down to this relationship where we have a logarithm right here, a natural log of v2 over v1. And so that's a pretty cool or pretty good relationship to observe. Let's see, let me put it that way. And I gotta wonder if maybe I messed up my curve right in here by not having, yeah, I might have, let me see here. No, it was fine. It wasn't necessarily, I didn't put the equation there. I just put the, this relationship into there with the n. That's all I did. All right, so while we're talking about processes, because we talked about I just mentioned a polytropic process. Something I made for myself a while back, and then when I taught a class in marine engineering at Coast Guard Academy, I decided to share this with people. Here's all the different processes for an ideal gas, right? And I'll show you where I got these from. But anyway, we could have a constant pressure on a closed system. Constant, and so let's see, well, the pressure is equal to pressure. Temperature now, this is just ideal gas law. Some of these are very simple, you don't need to know them. Some of these other ones, we will learn them, and they'll be useful to us. So it's kind of nice to have them all in one place. So you see what the work is when you have a constant pressure. We just learned that. We can also work it itself out with the ideal gas law to figure this out as well. Of course, we haven't covered entropy yet, so we would need to learn this and able to use that. For a constant volume process, work is equal to 0. We'll talk about that here soon, but that's because remember that the definition was work is equal to pressure times change in volume. If the volume doesn't change, the work is 0. Constant temperature process. So it kind of makes sense. We have a constant pressure, constant volume, constant temperature. So by the way, this is called isobaric. This is isometric, and this is isothermal. I think also there's another name for the constant volume. Well, we'll also cover what isentropic means. And what adiabatic means. Reversible adiabatic. Sometimes they're both things. Sometimes they're not. But here you go. Here's the polytropic of a closed system. So here's what we just talked about. We're like halfway down the page, and here's where we've introduced a process. That's one of the reasons why I'm even bringing this up. But you can see, like right there, that's the thing we just showed, right there. But we haven't shown the temperature part. One of these. You can have a polytropic process where it's constant temperature, by the way. Let's see. We have that anywhere up here? Well, I guess right there. No, right in here. I guess you'd say that n was equal to 1 when you had a constant temperature process. We also have isentropic for steady flow systems, which are different from isentropic for closed systems. And we'll learn about that sometime soon. Here's a polytropic for a steady flow system as opposed to the polytropic for a closed system. And we could observe what some of those differences are going to be from this. And then last we have a throttling process. So the source of this was this FE or Fundamentals of Engineering Exam Review Manual. It used to be called the EIT Manual, and here is mine, the 1991-92 edition right here from Lindenberg. This has been a great resource to have. See, these are called. I'm trying to not lose my page. I have to put a pen in there and raise this up. It's worth taking a look, and it's worth considering taking the Fundamentals of Engineering exam, which was called the EIT when I took it back in 1992. Anyway, it's got a lot of great sections in it, and it really just gets down to the point and a lot of things. Some stuff is just a great review. Some stuff, if you didn't know much about it, here's some manometer stuff. I'm trying to find some random things that might interest you. If you need some electrical, just, not advanced stuff, but just basic kind of things you want to review, you're going to learn in fluids, you're going to know what a pitot tube is, an equation to get what the flow is, if you have that. Just a lot of great stuff. Open channel flow, which is a civil engineer thing. Anyway, you get to this section here where changes in thermodynamic properties, and the one I really liked or thought was really good was the property changes in ideal gases. And here's where they went through, and they went through exhaustively went through all the different processes right here. So I went ahead and I had scanned this a while back, and then I just clipped all of these different equations and put them all into one sheet, and thinking that would be a nice thing to have just around. So you didn't have to memorize all of them or look it up every single time. I think other professors would wouldn't want you to have it, and would prefer that you would just think your way through them all the time. But I found this to be maybe a different way to approach that. Let's see, anything else I want to say about this before we go to examples? See, things that I said. I showed the cheat sheet, and you want to compare this to, let me put this down. Oh, wrong one. Compare to, let's see, all right, I could write in red. Compare to the ideal gas law, right, where we have PV equals MRT. Well, if n equals 1, right, for this right here, you could say that all of that is equal to a constant, right? If temperature doesn't change, m is a constant, r is a constant, t is a constant, therefore P times V equals a constant is probably going to be temperature equaling a constant. Suppose you could make the mass change, but we would never do that. And one last thing, this, so I want to address that concern. Let's see, I'm going to come up into the book, and this is section 3.4. Work as a path function. We talk about the polytropic process, and here is what I wanted to point out to you. So they can phrase it better than me, so I'm just going to I'm just regurgitating what they're saying. So note that the equations, let's take a look at those equations up above. They're saying in the polytropic process, in this one right here. So I didn't do a good job of that. So you'll notice they didn't say work when in there. So I have to apologize for having put this work here and work here, because they didn't do it. They didn't put it right into there, and they didn't put it right into there. And they say, note that we did not say that the work is equal to the expression given in these equations. These expressions give us the value of a certain integral that is a mathematical result. Whether or not that integral equals the work in a particular process depends on the result of a thermodynamic analysis of that process. It is important to keep the mathematical result separate from the thermodynamic analysis, for there are many situations, in which work is not given by that. So anyway, I wanted to bring it up because this was news to me. And so I want to be on the lookout for it, and you should be on the lookout for it as well. That we're going to try to find those many situations in which work is not given by equation 318, which is Up here somewhere. 318. 318. There it is. Okay, that's all. Something worth knowing.